The lights do not flicker first. There is no rolling brownout, no warning siren from the sky. 1 second the grid is alive, saturated with invisible current, humming behind walls and beneath streets. The next second, it is silent. Screens go dark. Engines stall. Elevators freeze mid-shaft. Air traffic control scopes blink out. In that fraction of a second, the architecture of modern life, built on uninterrupted electricity, stops breathing. This is what a large-scale electromagnetic pulse would feel like at ground level. Not fire, not spectacle, silence. An electromagnetic pulse is not a cinematic weapon. It is a physical event governed by measurable laws. In the case of a high-altitude nuclear detonation, gamma radiation interacts with atmospheric molecules and knocks electrons loose through the Compton effect. Those electrons accelerate along Earth's magnetic field lines, generating an intense electromagnetic field that spreads across vast geographic areas. That field induces voltage surges in conductive materials on the surface. Power lines, transformers, circuit boards, antennas, vehicle wiring harnesses, anything capable of carrying current can become an entry point for destructive energy. In the case of a solar superstorm, the mechanism differs, but the outcome can converge. A coronal mass ejection from the sun distorts Earth's magnetosphere, inducing geomagnetic currents in long transmission lines. The timescale is slower, but the infrastructure stress can be equally catastrophic. The common misunderstanding is that such an event merely turns off electronics. In reality, the initial phase of a nuclear EMP, known as E1, lasts billionths of a second, yet can reach tens of thousands of volts per meter. That is enough to overwhelm microelectronics before protective devices react. The second phase, E2, resembles lightning, but arrives too rapidly after E1 for standard surge protection to be effective. The third phase, E3, unfolds over seconds to minutes and drives geomagnetically induced currents into long conductors like high-voltage transmission lines. Those currents can saturate transformer cores, overheat windings, and cause permanent damage. Extra high-voltage transformers are not stored in bulk warehouses. They are custom-built, often overseas, with lead times measured in months under stable conditions. During widespread infrastructure collapse, global manufacturing and shipping chains would be compromised simultaneously. What remains hidden in public imagination is not secret knowledge, but systemic fragility. Modern infrastructure is optimized for efficiency, not resilience. Power grids operate on real-time balancing of generation and load, synchronized by precise timing signals frequently derived from GPS satellites. Water systems rely on electrically powered pumps to maintain pressure and elevate water into storage tanks. Telecommunications depend on powered towers, fiber amplifiers, and data centers cooled by energy-intensive systems. Financial transactions move through digital networks, requiring uninterrupted server operations. Remove stable electricity, and these systems do not degrade gracefully. They fail together. History offers controlled glimpses of this vulnerability. In 1859, during the Carrington event, telegraph systems, then the most advanced electrical network in existence, sparked violently under geomagnetic stress. Operators reported shocks. Equipment caught fire. In 1989, a geomagnetic storm collapsed the Hydro-Quebec grid in under 2 minutes, leaving millions without power. Transformers overheated in distant regions. That storm was moderate compared to the 1859 event. Since then, society's reliance on microelectronics has grown exponentially. The complexity that increases convenience also increases exposure. In the first hours after a continent-scale blackout, confusion dominates. Traffic lights cease functioning, leading to gridlocked intersections. Fuel pumps stop because underground storage tanks require electric motors to move gasoline to the surface. Even if a vehicle survives the pulse, something that testing suggests is possible for many models, The supply chain that feeds it stalls. Airports ground flights. Rail systems halt. Hospitals switch to generator power. But generators are finite machines, dependent on diesel deliveries that require functioning logistics networks. Water is the next threshold. Municipal systems depend on electric pumps to move and treat water. Elevated storage tanks provide temporary pressure, but once depleted, flow diminishes. Wastewater treatment plants rely on aeration systems and control electronics. Without them, untreated sewage accumulates, risking environmental contamination. The public perception is that infrastructure is durable because it appears solid. Steel towers, concrete plants, thick cables. The hidden reality is that its lifeblood is electricity. Food distribution follows a similar pattern. Urban grocery stores typically hold only a few days' supply under normal consumption. Refrigeration failure accelerates spoilage. Just-in-time inventory systems that restock shelves rely on digital ordering platforms, trucking fleets, and fuel availability. Panic buying compresses depletion timelines dramatically. Within 72 hours, densely populated areas can experience acute scarcity. Caloric deprivation is not immediate starvation, but it erodes stability. Hunger amplifies tension. Social order becomes fragile when basic needs are unmet. The science of survival in this environment is not mystical. It is procedural. Water safety becomes the first priority. Most surface water sources contain microbial contaminant. Boiling water at a rolling boil for at least 1 minute inactivates bacteria, protozoa, and most viruses. At higher elevations, longer boil times compensate for lower boiling temperatures. Mechanical filtration rated to 0.2 microns removes protozoan cysts and bacteria, but may require supplemental chemical treatment for viral pathogens. Chlorine dioxide tablets, when used according to concentration and contact time guidelines, can neutralize viruses effectively. Turbid water must be pre-filtered through cloth or sediment filters to improve chemical efficacy. These are microbiological principles applied under constraint. Sanitation becomes equally critical. Without functioning sewage systems, improvised waste management must prevent contamination of water sources. Human waste should be isolated at safe distances from wells or surface water, with adequate soil coverage to reduce insect vectors. Pathogen survival varies with temperature, moisture, and soil composition. Failure in this domain leads to secondary outbreaks of gastrointestinal disease, which historically have caused more deaths after disasters than the initiating event itself. Communication in a grid-down environment exposes another overlooked layer of resilience. Cellular networks depend on powered base stations with limited battery backup. Internet infrastructure relies on energized routing hardware. Amateur radio, however, can function independently using localized power sources. High-frequency radio waves can reflect off the ionosphere, enabling long-distance communication without satellites. This is not nostalgia. It is atmospheric physics. Operators equipped with protected radios and independent power can maintain situational awareness when mainstream channels are silent. Protection of small electronics depends on Faraday shielding principles. A conductive enclosure redistributes electromagnetic fields around its exterior, reducing internal exposure. Effectiveness depends on continuous conductive surfaces, minimal gaps, and appropriate grounding. Even improvised metal containers can provide partial shielding if seams are electrically continuous. The principle is simple. Prevent induced currents from forming within sensitive circuits. Medical realities escalate the urgency. Hospitals are engineered for reliability, but not indefinite autonomy. Backup generators typically sustain critical systems for limited durations, constrained by fuel supply. Sterilization equipment, refrigeration for medications, ventilators, diagnostic imaging devices, all require power. In prolonged outages, triage shifts from high-tech intervention to basic wound care, infection prevention, and resource allocation. Insulin storage becomes a life-threatening issue for diabetics. Dialysis patients depend on electrically powered machines multiple times per week. The fragility of medical dependence becomes stark. As days extend into weeks, infrastructure decay compounds. Refrigerated warehouses lose inventory. Fuel refineries, which depend on complex control systems to maintain safe pressure and temperature conditions, cannot restart instantly after uncontrolled shutdown. Restart procedures require stable power and coordinated logistics. Without them, fuel scarcity becomes systemic. Agriculture faces delayed planting or harvesting if mechanized systems lack fuel. Livestock operations reliant on automated feeding and climate control struggle to maintain animal welfare. Psychological stress overlays physical scarcity. Human cognition degrades under chronic uncertainty. Communities with pre-existing networks of trust demonstrate greater resilience, as observed in disaster sociology research following earthquakes and hurricanes. Mutual aid reduces violence and accelerates stabilization. Isolation increases risk. Preparedness is therefore both material and social. Energy independence at the household scale offers limited but meaningful leverage. Solar photovoltaic panels convert sunlight into direct current electricity via the photoelectric effect. Charge controllers regulate energy flow into batteries, preventing overcharge and thermal damage. Battery chemistry matters. Lithium iron phosphate cells provide thermal stability and longer cycle life compared to other lithium variants. However, electronics within inverters and controllers remain vulnerable to electromagnetic damage unless shielded. Redundancy and protection determine survivability. Urban high-rise dwellers face distinct hazards. Water pressure drops first on upper floors. Elevators cease functioning. Fire suppression systems reliant on electric pumps become unreliable. Evacuation requires physical descent in darkness. Stairwells become choke points. Mobility and physical fitness, often overlooked in preparedness discussions, become survival variables. Throughout this progression, the pattern remains consistent. Interconnected systems amplify cascading failure. The absence of electricity is not merely inconvenience, it is systemic paralysis. Recovery timelines depend on the scale of damage to high-voltage transformers and control systems. If replacements are limited and manufacturing capacity impaired, restoration could require months or longer. During that period, survival shifts from emergency response to sustained adaptation. The critical insight is that resilience is proportional to decentralization. The more essential functions, water purification, food storage, communication, energy generation, can operate independently of centralized infrastructure, the greater the survival margin. This is not a call for isolation, but for redundancy. Engineering disciplines call it fault tolerance. Biology calls it adaptation. In a grid-down scenario triggered by electromagnetic disruption, adaptation is not theoretical. It is the dividing line between stability and collapse. When the grid fails without warning, civilization does not end in fire. It pauses in darkness. Whether that pause becomes temporary disruption or prolonged collapse depends on preparation grounded in science, infrastructure awareness, and disciplined response. The laws governing electromagnetic pulses are fixed. The question that remains is whether human systems, technical and social, are engineered with equal understanding of their own limits.